So we call this a sine wave, and we know it well from audio synthesis. It's a pure tone at a given frequency. But then you might think back to high school and remember sine and cosine having something to do with triangles and figuring out angles. How are these two things related? Let's find out. Hi everyone, welcome back to Sound and Voltage. I'm Jeff. You may have been following along with my series on frequency modulation and FM synthesis, and in that series we're getting to the point of digging into the math that underlies it. But as I was planning that video, I thought that maybe it made sense to pull out this topic in particular and look first at just what a sine wave is, and where it comes from, and how it relates to that high school trigonometry. In the context of that series on FM, the next video is going to go deep on the math behind it, and I'm going to be throwing around sines pretty liberally. I wanted to make sure that everyone could start with the same basic understanding. And this video is really aimed for people approaching it in that way. My goal is to provide synth nerds with an intuition for what a sine wave actually is and where it comes from and why it works the way it does. If you're not watching that series and you just saw the title and wanted to learn more, it's still a pretty interesting topic. Just know that I'm not trying to be comprehensive here. I'm not aiming to teach people everything they need to know to pass an exam or anything. But I hope that, in conjunction with other material, you'll find a lot of this interesting and helpful. And if you end up really liking this sort of thing, leave a comment and let me know. I'm a fairly big math nerd, and I never mind a reason to get into it. And I suppose that sets up the inevitable request for you to like and subscribe and ring the bell and swing a chicken over your head 4 times in a clockwise direction. It really helps the channel out. Now, the likelihood is that, outside of synthesis, the last time you thought about sine or cosine was math class in high school, and it probably came in the context of a triangle like this, and trying to work out what the angle here is, and you might remember a mnemonic for how they work, something like SOHCAHTOA. And that's cool. It teaches you how to calculate trig values based on the lengths of the sides of triangles. For instance, it tells you that the sine has something to do with the ratio of the opposite side, over here, and the hypotenuse here. That might not come up a whole lot, but it's easy to remember, and maybe sometime 20 years from now it'll come up. But it doesn't really tell us what sine is, deep down, and it certainly doesn't explain why we call this a sine wave. And to some extent, that's because we tend to teach it backwards. Sine isn't really about triangles, it's about circles. Well, it's about a specific type of triangle, one that fits inside of a circle. So here's a circle, and I'm going to put a point at the origin, at the center of the circle, and I'm going to put another point out here on the perimeter. Then I want to look straight down from that point on the edge and see where it lands on the x-axis. That's the vertical center of the graph. And we'll put a point there. Okay, we've got 3 points, so let's join them all with lines, and there we go. This is our special type of triangle. It's a right triangle because we dropped this line down perpendicular to the x-axis, and the length of the line, the hypotenuse of the triangle, is the radius of the circle. It's common for us to refer to this radius as r. You might remember something like the perimeter of a circle being equal to 2 pi r. That's the r we're dealing with here. And then we tend to concern ourselves with this angle down here, between the x-axis and what's now the hypotenuse of our triangle. That angle is often called theta, the Greek character, and like a lot of things in math, we just call it that mostly as convention. Okay, so now the diagram has all the parts we really care about, and it doesn't really matter where that line out to the edge ends. It could be here, or here. As long as we've got a line out from the center to the edge, we make a right triangle out of it. Everything else is going to work the same way. Let's just place one more restriction on our circle and our triangle. It's an important restriction. Let's just assume that the radius, the value for r here, is always 1. It doesn't really matter what it's 1 of, 1 inch, 1 mile, the length of 1 banana. We just agree to call it 1, and that makes this a unit circle. And now that we've got that, something interesting happens. Remember when we described sine as being the ratio of the opposite side here, and the hypotenuse? Well, now we know how long the hypotenuse is. We just agreed that it's always going to be equal to 1. So let's call the length of this opposite side here y. Well, if the sine of that angle, the sine of theta, is equal to the length of that side, divided by the length of the hypotenuse, y divided by 1 equals y. So the value of the sine function, when the radius of the circle is 1, the value of that sine is just the length of this side of the triangle. And that's one side of the triangle. How about the other one? Let's call its length x. And we know that from our mnemonic that the cosine of the angle is equal to the adjacent side, that's what we just called x, and divide that by the hypotenuse, which is 1. So the cosine of theta is x over 1, or just x. Wow, okay, so we just went from thinking about sine and cosine as having to do with triangles, and now we see that they're actually identifying a point on the circumference of a circle. So it'll be interesting to see just how the value of sine changes as we go around that circle. We can start just by looking at it here. We can start with the 0-degree angle. That's just a straight line out along the x-axis. It might seem more natural for the top to be 0 degrees, but for math reasons, we're going to start in this direction. And we can tell just by looking at it that the x value, which is the cosine, that's going to be 1. And the y value, the sine, is going to be 0. It doesn't go up at all. Now we look at a 90-degree angle, and we're pointing straight up. X, the cosine, now that equals 0 because we're not going anywhere along the x-axis. And y, the sine, is now equal to 1. We go to 180 degrees, and we've got the cosine that heads out to the left at -1, and the sine is back to 0. And 3/4 of the way around at 270 degrees, the sine is down at -1, and the cosine is back to 0. If we keep going, it's just going to wrap back around. Now, degrees are easier for humans to think about, but that's not how the universe thinks about it. We're going to start measuring angles differently in a minute, but before that, let's just dig a little deeper into how the sine value, the height of that point along the edge, changes as we go around the circle. Wow, yeah, okay, there we go. There's our sine wave, and it's created just by working our way around the circle. There really are 3 variables when it comes to describing a sine wave. There's amplitude, which is the maximum distance away from 0, and here we're just sort of using the natural default amplitude. Because the unit circle has a radius of 1, the values for sine are restricted to be within 1 and -1. The second variable for our sine wave is frequency. If we rotate around our circle faster, then we go through our sine wave pattern faster, and that increases the frequency. If we go through it slower, then the frequency drops. If we slow all the way down to 0, that would just result in a 0 Hz frequency, which, when we talk about an audio signal, is just a fixed DC voltage. Now, if we reverse direction, start going around the circle in the other direction, then it basically looks the same. But we're going in reverse now, and we consider that a negative frequency. The idea of a negative frequency really hurt my head until I could see it like this and watch the rotation start to go in the opposite direction. For the most part, we can treat this as if it were a positive frequency, just with a phase change. And that's the third variable, phase. We often see it come up when we look at 2 sine waves of the same frequency, like here. It's clearly the same shape. The only difference is where they are in their respective cycles. That position, that angle, is the phase of the wave at that time. In this specific case, where the 2 phases are 90 degrees apart, that's a special case because that makes the top one the sine wave and the lower one the cosine. The 2 of them, sine and cosine, are the same thing, just with a phase shift. It might not be immediately obvious that sine and cosine are going to take on all the same values just at different times, but both of them just reflect points around the perimeter of the circle, and the circle looks pretty much the same no matter which way you look at it. Let's look quickly at the relationship between how fast we sweep through the circle, how fast the phase is changing, and the frequency of the resulting sine wave. If the phase is changing quickly, the frequency is high, and if the phase is changing slowly, the frequency is low. And it's cool. For people who have just a little bit of calculus background, this might start to sound like a derivative. In fact, it is a derivative. Frequency is the derivative of the phase with respect to time. And maybe it's just me, but that was an eye-opener for me when I first saw it. But I'm not going to go any deeper into calculus than that for this video. And now I'm going to address the thing that's had mathy folks gritting their teeth since I started. Until now, I've been talking about angles in terms of degrees, like a right angle being 90 degrees or a whole circle taking 360 degrees. The use of degrees to measure angles actually goes all the way back to the Babylonians like 4,000 years ago. They didn't know advanced math, but they knew they needed a way to divide a circle up into pieces, and they already used a base 60 numbering system. 360 wasn't a stretch, and it's great because it's divisible by almost everything. But as mathematics developed, it became more natural to express angular measures in terms of the circle itself. We've been using the unit circle all this time. It has a radius of 1, and that makes the circumference, we've calculated that as 2 times pi times the radius, just equal to 2 pi. And it turned out that just treating the angle as if it were the same as that arc length, so that means it's 2 pi radians around a circle with a circumference of 2 pi also, ended up just making things way simpler. Now we have a single value that reflects both the angular measure as well as the linear measure of the arc length. And instead of having to force things in and out of a human-defined system of 360 degrees, we're staying close to the definition of a circle in order to work with circles. Funny how that works out. So for future videos, I'm going to be working in terms of radians with 2 pi of them equaling a whole circle around. And I wanted to make sure I got to that because in the upcoming video, when I dig into the math behind frequency modulation, there are 2 pi's all over the place, and I wanted you to know why. Okay, I think that wraps up what I wanted to cover in this video. We started by looking at how we're often introduced to sine and cosine in terms of working with triangles. But then we saw that it's really about circles, and in particular about how sine and cosine act as the y and x coordinates of the positions around the circumference of a circle. Then we saw that if we rotated through the circle, the graph of the y coordinates of sine, it would create that famous sine wave curve that we know so well. We talked about how the speed that we go through the circle decides the frequency of the wave, and how that really amounts to the rate of continuous change in phase. And finally, we wrapped up by explaining how we don't use degrees as measurements of angle in this kind of math. Instead, we use radians, which are much more natural mathematically, even if it does force us to start using 2 pi's all over the place. Like I said at the start, I really didn't intend this video as a full description that might get you through your math class. Instead, it's really aimed at people doing audio synthesis to better understand where that sine wave comes from. But my hope really is that there's a lot here to help any student develop an intuition for the concepts of sine and cosine, what they really mean. If you think I hit that mark, maybe drop a comment. And definitely, if you've made it this far, maybe like and subscribe so you'll see the next video when it drops. Thanks for watching.